About this static situation that I gave you. We have this influencer that's balancing on this beam. Now, this isn't a realistic situation because the beam has negligible mass. We will do one with more realistic situation where you have to take into consideration the mass of the balancing beam as well, because that puts another force on it. So we're not considering the weight of the beam because that's an additional force. So this is a situation with three different forces. And so we want to identify those three forces. So we have, first of all, the weight of, let's go with a little bigger, the weight of the barrel, mg. So we'll just call it W barrel. And then we have the weight of the influencer, Wi, and that's a mg as well. And then those are both downward. Then we have a force upward, and that's a force of tension on the rope. So we have three forces acting on this. If we had to take into account the mass of the beam, we'd have a fourth force acting on it. In this case, we're not worried about that. We know the length of the beam, we know how far the influencer is away from the rope, and therefore we know how far the barrel is away from the rope because they're on opposite ends of the beam. So what we're looking at then is a net force equation. Well, our net force equation is these three forces add up to be zero, which means one of the three forces has to be in the opposite direction of the other two. You cannot have all three forces in the same direction because that wouldn't be a net force of zero. So in this case, obviously, the rope is acting in the opposite direction of the weight of the other two. So we can still write WB plus force of the tension plus weight of the influencer equals zero. That's our net force equation. We could write, if we wanted to, Ft equals WB plus Wi, or it equals negative WB plus Wi, I should say, because they're in opposite directions. But this is a way to write this. So we're looking at our slide here that tells us how to solve static equilibrium problems. So our net force equation is just accounting for all the forces, and all the forces have to add up to zero. So you can just write it like that. Then we have to choose the axis of rotation. And we could choose any point on this. We could choose a point that is not where forces are, right there. But it's easiest if we choose a point that's in where one of the forces is acting on it. And the reason is because then that particular force is not putting torque on it because the lever arm length is zero. So the best way to do that then is you pick a place where we do not know how much force there is. If we have a situation with three forces acting on something and we pick a pivot point that is at one of those three forces, that means the other two forces have to equal each other in terms of the amount of torque, but opposite in direction. So the natural point we would generally pick is right here, where the rope is connected to the beam, but it doesn't have to be. We could pick where the influencer is. Now, that's probably not where it's going to pivot, but it doesn't matter. Mathematically, it can work. We could also pick where the barrel is, but I would avoid picking where the barrel is because that is the one spot that we actually know the mass of something. So if we pick where the barrel is, we can get the ratio of the forces from the influencer and the rope, but we cannot get the actual numerical values because we've already gotten rid of one of the torques that can be calculated. So I'm going to choose that point where the rope connects because I don't know how much force is on the rope. So my net torque equation then would be, it would be writing it like this. Weight of the barrel times, in this case, 0.75 meters plus, and that is putting a torque on the system in one direction. So plus the torque of the system in the other direction, weight of the influencer, times 4.25 meters. In other words, we have a ratio of the two weights that is inversely proportional to the distance from the pivot point. When we have three forces, we pick one of the forces being the pivot point, and that gives us the way to calculate what the other forces are, because that means they have to cancel each other out and balance out. All right. Since we know the weight of the barrel, we can solve for the weight of the influencer just by plugging this information in. We know the mass of the barrel, so the weight of the barrel is mass times acceleration of gravity in this case. So what we can do then is plug that in if we want to. Now, if I had taken, that's for this pivot point, if I had made this the pivot point, the influencer, I could write an equation like this. And I could do weight of the barrel times, now it's 5 meters away, plus the tension I guess I put F sub T, times, well, that's 4.25 meters away. And those combine to equal zero torque. All right? It doesn't matter. Either one now I can solve for because I have a ratio. In fact, this would be the one that you could directly use to solve for the tension on the rope, and the purple one is the one that I could use to solve for the weight of the influencer, or the mass of the influencer. All right. Once I've solved for the unknown of either one of those, then I just use my net force equation here to solve for the other of the three. So I'm going to use this one right here. If we have more forces, then we have to do more equations and do different substitutions, or we can do a system of equations, and we'll do that as an example when we actually have to take into account the mass of the object that they are balancing on. But here, since I know the weight or the mass of the barrel, 375 kilograms, I can solve for the weight of the influencer. So if I rearrange my equation to solve for weight of the influencer, I get this right here, weight of the barrel, 375 times 9.81 times 0.75 meters over 4.25. Now notice the meters cancels out. I'm going to get kilogram meters per second squared, which is the same as newtons. And when I calculate that out, I get 649. If I want the mass of the influencer, then 649 divided by 9.81. And I get 66.2 kilograms. right? That means then that I can use this equation here to solve for the force of tension. So the force of tension is equal to, in its opposite direction, so that's equal to negative W of the barrel. I should put negative there, plus the weighted influencer. So the negative is just telling us direction here. It's not really critical that we put that in like that. But we can take 649 newtons plus, I guess I'll continue this trend here. And the 375 times 9.81 is 3678, so 3680. So that means that the tension that the rope needs to withstand is the combined weight of those two, which is 4,330. All right. So this is a simple one. When we have three forces, we can just substitute or solve, but you got to make sure you pick the right equation. There are three different equations that we could use. The third equation is the absolute wrong one, and that would be solving for the torque at the barrel with the pivot point at the barrel, because we don't know the force of tension on the rope and we don't know the weight of the influencer, but we do know the mass of the barrel. But it would be a valid way of getting the ratios of them, but it wouldn't solve for that, right? So that's how we approach those solutions to get the mass of the influencer in this case and the tension that the force of the rope needs to withstand.